So we talked about the fact that events are sets, and for that reason, we talked a little bit more about sets. And the last step in defining a probability model after we specify the sample space, the outcome, the event, is to assign probabilities to the events. And all that means is we're assigning numbers to the events, and those numbers represent how likely the event is to occur. Probability is a very broad framework. It's meant to, and it does, accommodate all sorts of ideas about uncertain situations. There's really nothing you can't model with within the probability framework, but there are 3 axioms, the Kolmogorov axioms, subject of this lesson, that those numbers that we assign to our events have to obey in order for the whole system to make sense. Okay. So axioms are things that are sort of like ground rules that we're just agreeing to at the outset. And so let's talk about them. So the first one says that for any event E, the probability of E is a number between 0 and 1. Okay, so there's no natural units for probabilities. The way we make the magnitudes make sense to us is we have an upper bound and a lower bound to them. Second axiom says that the probability of the sample space is 1. Okay, something's got to happen. If you have set your sample space up correctly, the probability of the sample space should be 1. If it's not 1, it means you either left something out that can happen, or you've got something in there twice. There's like a logical problem with the whole thing. So first 2 axioms, kind of straightforward things that I think you already knew about probabilities. The third is got a little more content to it. So the third axiom says, let's say we have some events, event 1, event 2. How many of them? Oh, there are n of them, some set of events here. And let's say they are all mutually exclusive. And just reminding ourselves, what does that mean? Mutually exclusive says that pick any EI and any EJ, pick any of those sets that you want, and the intersection of those two will be, didn't mean to draw that, will be the empty set. Okay. No overlap between any of the EI and EJs there. Okay, so let that be true. Then, when that is true, the probability of the union, as I goes from 1 to n, of the EIs, okay, the union of all these mutually exclusive events here, the probability that one of them happens is sum of the probabilities of the individual events. Okay, so that's kind of cool. Just to wrap our brains around what's going on here, let's think about the case where n is 2, where we've just got 2 events here. Okay, so let E and F be mutually exclusive, just like the axiom says. Then if I want the probability of E or F, it's just the sum of the probability of E and the probability of F. Okay, so that's pretty cool. You might be wondering, okay, well, what happens when the events are mutually exclusive? We've got an answer to that, but it doesn't have to be an axiom, okay? You'll see that we can derive an answer for the broader case just by using these 3 axioms. So we're going to get to that very, very quickly. Before we do, let's just kind of apply that Kolmogorov axiom one more way. Or really, let's notice how something we've kind of already been doing is an application of that axiom here. So let's go back to our example with the probability, with the parties forming the government And let's think about the event that party A is in government. Okay, so in our example, we could list the outcomes that made up that event. Okay, it could be a government of A and B, of A and C, national unity government, or a minority government with party A. One way to partition this event, and any event that's composed of discrete outcomes, is just to make each outcome its own event, right? Okay, so let's just do that here. And let's say I'm going to calculate the probability of event A as the probability of AB plus the probability of AC, probability of ABC plus the probability of A. Okay. So what I've done here is I've taken set A and I've partitioned it into 4 events here, each of which has a single outcome, and they all have a single different outcome. So yes, they are mutually exclusive. And I figured out the probability of the bigger event by just adding up the probability of each outcome. Okay, so that's a totally legit thing to do. It's what the axiom tells us we have to do. This is kind of so concrete that you might be wondering, well, why isn't that the axiom? Why doesn't the axiom just say the way to calculate the probability of an event is to sum up the probabilities of each outcome in the event? The answer is that we can't always sum up the individual probabilities when our event is a subset of the real line. Okay, then we can't just sum up all of the events, because there's always, no matter how close we get with individual numbers, there's always a whole bunch of numbers in between. So this isn't possible. And the whole logic of defining events as sets is meant to accommodate the idea that we want to be able to talk about sample spaces that are subsets of the real line. The sample spaces you guys are going to be most interested in as data analysts are going to be defined on the real numbers. You guys are interested in, the estimates that you get from your data, and those are real numbers. So probability sample spaces that are continuous in that sense, where we can't identify the individual outcomes, are going to be important for you. And we're going to get to them about the middle of the quarter. We're starting off with discrete probability models where we can actually list the individual outcomes, because it's just kind of one thing at a time, easier to wrap our brains around the basics of probability before adding in the additional trippiness of real numbers. Okay. All right, so that was a little set of comments on the third Kolmogorov axiom. Let me get back to my main point here. There's just those 3 axioms. Everything else that we want to do with probabilities, every other rule, every other process, every other manipulation, we can justify in terms of the Kolmogorov axioms, what we know about set theory. That's why we just did those lessons on set theory, and what we know about real numbers. So thinking about some rules of that apply to probabilities, those rules can all be derived, they can be proved using those 3 ingredients, using the Kolmogorov axioms, set theory, the rules of real numbers. So examples of the kind of rules I'm talking about that are consequences of Kolmogorov axioms. One is that the probability of E complement is 1 minus the probability of E. Okay, again, something that you probably already knew, but we don't have to assume this. Okay, this, if you accept the Kolmogorov axioms and accept the rules of set theory and the rules of real numbers, which you should, this follows. This has to be true. Another rule here, another consequence of the K axioms that's always true for probabilities, which is that if event E is a subset of event F, then it must be true that the probability of E is less than or equal to the probability of F. Okay, so this little rule gets out the problem in the is it more likely that Jane is a bank teller and a feminist than that Jane is just a bank teller? Example. Okay, that's that claim that lots of respondents in Kahneman and Tversky's experiments said they believed violates this rule. Okay, the event that Jane is both a bank teller and a feminist is a subset of the event that she's a bank teller. So it cannot be more likely that she is both of those things than that she is just one of those things. Okay, so that's a consequence that follows from the basic axioms of probability. And then the third consequence, getting back to a question we raised earlier, what do we do when we want the probability of a union of sets that aren't necessarily mutually exclusive? Well, this is what that probability is. It is the probability of E plus the probability of F minus the probability of the intersection. Okay, so what we have here is we have the rule for probability of an arbitrary union. Okay, so we're not restricting it just to the cases where E and F are mutually exclusive. Here, we're allowing for the fact that they might have a non-empty intersection, and this is how we incorporate that into the probability of the union. Okay, but again, we didn't have to make an assumption about that. This follows from the axioms that we have. Okay. So you're going to have a chance to work out some of the derivations of these consequences in the quiz and the workshop for this lesson.